Okay, so welcome everyone to our usual Wednesday seminars. And today we are delighted to have Falk from the University of Wroclaw, who will tell us about the complicated integrability structures, the generalized geometry of alpha prime corrections,
Yes.
both in string theory and in sigma models.
Yeah, guys, thank you very much for the invitation and for giving me the opportunity to talk at this very nice seminar. So it's a pleasure. Yeah, and what I was asked for today is to tell you something about our most recent paper, so where we have done some calculations to figure out how alpha prime corrections in string theory can be better understood from some more geometrical point of view. So this is the idea here. So let me just quickly lay out the problems for you. And of course, please, at any point when there is anything you want to ask or so, please stop me. And I'm very happy to just have a dialogue with you instead just talking to my computer. So, but you see, the problem, of course, is well known. I mean, we know that in principle, even when we look at GR, so the Einstein-Hilbert action is not renormalizable. So that means we have to add counter term after counter term after counter term. So in principle, we get an infinite number of counter terms. And usually, of course, in quantum field theory, so when we just have a finite number of counter terms, we can do some measurements to fix the coefficients in front of these counter terms. But here, of course, we would have to do an infinite number of measurements, so we lose any predictive power. But of course, probably some, at least hopefully, people in the audience will agree that there is a nice candidate of theory which is called string theory. And string theory, in principle, gives us some idea how a theory of quantum gravity might look like. Of course, it might not be the theory of quantum gravity, but at least we get some features. And in string theory, actually, we get all these higher derivative corrections, which we expect in an effective theory from two contributions. So there are G string corrections, which are really or can be understood as some loop diagrams, which take into account different genuses of the string worldsheet. But then also when you go to the worldsheet, to each explicit worldsheet of the string, so for example, even the sphere, then of course you put punctures in there, but then you calculate some kind of amplitudes or string correlation functions on this worldsheet. And they, of course, also can have loops. And so you get a second loop counting parameter, which is alpha prime. So that means in string theory, you usually get GS corrections and alpha prime corrections, and both of them will give rise to these higher derivative corrections, which we are interested in. So, and at this point, I could in principle stop my talk and I could tell you, okay, so everything you want to know, you will get from string theory. But of course, you also know that in principle, it's very complicated to calculate all these corrections because you have to do some string scattering amplitudes, for example, or some higher loop beta functions, which are both not very pleasant to work with, in particularly when you go to high orders. So, and what does it look like? Let me just show you in the leading order. So there we have our effective action. And here I'm just doing the NS-NS sector. And of course, in leading order, so you have just your Ricci scalar. Then you have a kinetic term here for the dilaton. And so you get a kinetic term for your H flux, which is just the field strength of the two-form B field. And that would be everything you would get at two derivatives. And then when you increase the number of derivatives and just look at the NS-NS sector, for example, for the heterotic string or the bosonic string, you will get four derivative corrections. And in principle, so there you have already seen that you get this Riemann square terms here. And here, I've just written it down in a symmetric way between the left and the right moving sector. So that means this minus here means with respect to a spin connection where I have not only the usual spin connection, but this minus the H flux and the plus here where you have plus the H flux. So, and you can write down these terms at four derivatives. And in principle, you can even put some coefficients in front of them, A and B. And also you get something similar for the H flux, which is corrected by a Chern-Simons term, again, for this connection with plus and with minus, which you can see here. And again, there are some coefficients A and B. And by tuning these coefficients, you can either get the heterotic string, so that means you have to set A to be minus alpha prime. You can get the bosonic string, where you have to set A equals B to minus alpha prime, so this is symmetric between the exchange of left and right. And of course, then you also know there are type 2 strings, where at this order, there is no additional correction. So that means you would set A and B equals to 0. And so in this way, and I think so this is an old story where, for example, I think first Accardi, who might be in the audience, yeah, I've seen him, has done some nice beta function calculations and have found these kind of terms. And this is just a nice universal way you can capture this leading order alpha prime corrections. And these are exactly the corrections I want to look at in this talk. I will not say more about GS corrections. But of course, now you can try to push this calculation to higher orders. And you have seen we had some terms here and we were fixing some coefficients. But the problem is that the higher the order, the more complicated the story gets. So for example, when you have just two derivatives, you will just get these three terms here. And it's pretty easy to fix three coefficients. When you get already four derivatives, you can write down 8 terms after you were modding out by all field redefinitions. So you have to fix 8 coefficients. And this is exactly what Accardi back then did in this paper. But now when you push it further and you have 6 derivatives, you already get 60 coefficients. So that means it grows extremely fast. And of course, this is not so nice, because at the end of the day, you get too much terms. And that also explains that nothing is really known about any theory with more than 8 derivatives. So we are actually blind at this point. And of course, that's a pity, because when you would like to do the full string theory, you should understand this thing, ideally to all orders. Okay, so this is the problem I want to deal with. And the basic idea behind this problem is actually that we want to leverage some symmetry to decrease the number of possible terms. Because the number of terms I have given you so far, they are just based on counting terms which are nice invariants under diffeomorphisms and B-field gauge transformations. So which are clearly the most basic symmetries this theory will have, and will have at all orders. But of course, you know, there are more symmetries. And for example, when we look at the super string, there is supersymmetry, SUSY. But you see, SUSY has a problem in that, in principle, it should actually fix a lot for us and should just really leave us with a highly constrained action. But for those of you who have worked a lot with SUSY, the problem is actually to write down the transformation laws explicitly and to find invariants, especially when they are corrected with higher derivative corrections. I mean, one very nice technique in supersymmetry is using a superspace, so which gives us a linearly realized supersymmetry. And there one can do a lot, but the problem is that superspace becomes much more complicated when the number of supersymmetries are increasing. And for this highly supersymmetric series, which we are dealing here with, there is not much which can be done. So that's why people try to find some alternatives to supersymmetry. And one alternative, which I want to talk about more today, and which is actually the main ingredient of the paper you asked me to talk about, is what is called generalized Lorentz symmetry. So it's an extension of normal Lorentz symmetry. And this symmetry actually has a natural motivation from T-duality. And so this is what we want to talk about today. And then, of course, you know, there might be some other symmetry principles which also might help us, but I will not say anything about them. Okay, good. So let me try to make this a little bit more explicit. And so I'm trying to give you as much details as I can, so that you really believe me that what I'm telling you is going to work. So the idea behind this extended generalized Lorentz symmetries is that we actually want to reshuffle the degrees of freedom we know from our supergravity theory. And here in particular for the NS-NS sector, we have a metric, but actually when we want to go to higher derivative corrections, it's better to use a frame instead of a metric. So we don't use the metric itself, but we use a frame. And of course, we have the B field. But we will not treat them as independent quantities because we know that T-duality mixes them. So that means we are combining them in an object, which is called a generalized frame. And this is actually what I've written down here. It has 2 times the components of the usual frame. And you see, for example, in this component here, we have the usual frame. Here we have a combination of the frame and the B field. And here we have the inverse of the frame. And then you see, of course, this is additional structure. And we want that this generalized frame is constructed in such a way that it is actually invariant under a structure which is OD, comma D, this one here. So that means this frame here is just an element of this group OD, comma D, and it will leave this metric here invariant. So that means when I multiply this frame from the left and the right with this metric, so doing transpose, of course, also, because I have to contract these A indices, which are flat indices, with the flat indices here, I will get the same result. So that's the idea. And then, of course, at the end of the day, I still want to extract my metric and my B field from this. So, and for this purpose, I actually have a second object, which is called the generalized metric, and I take it here in flat indices. And this thing actually will be invariant under a smaller transformation, which is OD cross OD. So that means a left moving Lorentz part and a right moving Lorentz part. And this smaller symmetry here, this will be exactly generalized Lorentz symmetry, because this is needed to actually take this frame here and just extract the physical metric and the B field. Okay, so that's the setting. So let me try to show you how this symmetry acts at the leading order and how we can extract an action from it. So of course we were saying all our degrees of freedoms are encoded in the frame. So that means what we have to do is I have to tell you how the frame transforms. And so there are 2 parts. So there is the generalized Lie derivative here. And this generalized Lie derivative actually will just generate diffeomorphisms, so which we of course know are needed to describe gravity, and it will also generate gauge transformations for the B fields, right? So these parameters are actually a vector and a one form. So this is one part, and of course this is natural again in a theory of supergravity, right? Because these are manifest symmetries which we always have. But then, since we were also using this frame, so we get a second symmetry here, which is this generalized Lorentz symmetry. And this actually lives in the subgroup OD cross OD. So, and this, from one point of view, when we want to understand it, tells us a little bit more how, for example, fermions would transform in the supergravity theory. So now we have the symmetry. And so now, of course, we want to find some quantities which transform in a nice and covariant way under the symmetry, right? This is always how the games work. So you fix a symmetry and then you start to discuss nice and covariant quantities. And here you see we have a problem because in principle we have 2 symmetries. So we have generalized the generalized Lie derivative here, so generalized diffeomorphisms, and we have generalized Lorentz transformations. When we ignore the generalized Lorentz transformations for a second, so it's not hard to find some nice quantities which transform like scalars here under generalized diffeomorphisms, which are called the generalized fluxes. And these are exactly these combinations here of derivatives. So this dA here is called a flat derivative, which is just the E contracted with the normal derivative. And then you can calculate this object, and this is a scalar under generalized diffeomorphisms, and another object here as well, which also takes into account the dilaton. So that means you have all your nice basic objects, and then what you can do is you can ask, is there an action which is a nice scalar, or at the end of the day, when I integrate it, even an invariant quantity under this symmetry? And the answer is yes. And what it will do for you, it will fix you the action completely, uniquely, up to a global factor. So that means, in principle, you just impose the symmetry, you will get a unique answer for this action, which is now nicely invariant under generalized diffeomorphisms, under the generalized Lie derivative and generalized Lorentz transformations. And so this, in principle, fixes the problem we encountered earlier, where I was telling you that you have to fix 3 coefficients. So we are going down from 3 coefficients just to a global overall coupling. So this is the story at leading order. And then, of course, when it works here, so we could, of course, ask, is there a way that we can also do something similar for higher derivatives? So this, at the moment, is the setup. May I pause here for a second, and may I check with you guys whether there are some questions, or whether this in principle, at least from the idea, is clear?
Well, I have questions, but
Okay.
let's hear the audience first.
Hello, Falk. Yeah, I have a
Hey.
question. So, yeah, I got a bit confused. So by saying Lorentz, so there is a Lorentz which is part of diffeomorphisms, but there is also Lorentz, I guess, like local Lorentz symmetry, which is kind of gauged in frame-like format,
Exactly.
right?
Exactly.
So where is this Lorentz sitting here?
So
Like
this
overall, I mean,
Lorentz, yeah, this is a good point. This Lorentz really acts on the flat indices, right? So that means it is really like the local Lorentz symmetry which you have when you work in a frame-like formalism. But now you see you don't have just one Lorentz symmetry, but you have actually this product. So you have, in a way, naively, when you think about the string, you have a left-moving and a right-moving sector. And so in the first approximation, you can understand it that you have a Lorentz symmetry for the left-moving sector and a Lorentz symmetry for the right-moving sector.
okay, so you're in Euclidean signature, so OD is Lorentz too.
Exactly. Yeah. Sorry, I'm here for the simplicity. Euclidean signature. You could always do it also in Minkowski, and then you would just write a bunch more of ones here and d minus ones.
Yeah, okay. So another question is like, I don't know, kind of philosophical. So I'm wondering, like, you are trying to make some symmetry manifest. So I'm wondering whether by doing this, you miss some opportunities where this symmetry is present but not manifest. Let's say probably it's there but cannot be written in terms of like frame fields, like localized symmetry.
You are right. I mean, so what I'm doing is in principle a little bit like guessing, right? So I mean, I'm trying to find a certain symmetry which is constraining enough, to give me, of course, still at the end of the day, what string theory gives me. But on the other hand, I'm of course not guaranteed that this works, right? So this is some idea. I will try, and I will later on explain you to which extent it works. But yeah, there might be a way to do this in a more general setting, or to do something else. But at the moment, I think this is the best way, as we understand it currently, to get something which at least partially works.
Yeah, so in principle, it's imaginable that there are actions with this symmetry, but which cannot be written in these terms.
There might be, yeah, there might be. I mean, of course, when you have T-duality and when you compactify things on a torus, so I think there is work by Ashok Sen, for example, which proves that you have to get some global OD, D symmetry. But here you see we are pushing it a little bit further, because we are trying to find this symmetry even before the compactification, and we try to make some of it even local, so which is this OD cross OD, for example. So that's the setup. Yeah, but I agree. I mean, you might do other things, but at the moment, and so that's good that we talked about it. So that's what we are doing. And you see, the main question which I am thinking about a lot actually is, can we do something similar and can we also get the higher derivative corrections? Because here it's quite simple, right? I just go down from 3 parameters to 1, but then of course when I would push it further, I would just reduce much, much more parameters, hopefully, and then so this would become easier. Okay, good. And to do this, actually, we need some tool. Because what I'm telling you is, so we try to find some symmetry. So, and in principle here, the examples were that we have generalized diffeomorphisms and this generalized Lorentz symmetry. And then we have some kind of machine, some big machine where we put the symmetries in and we ask this machine for invariants under the symmetry. Because the invariants are actually the quantities which we use to get our action. So, and this is actually always the kind of procedure. So we start with a symmetry in a way that we postulate and we want to have invariance. And you see, so there's a nice machine actually, which we now call generalized Cartan geometry, but which also can be or is known as something like Polacek-Siegel construction, or for mathematicians it might be known as symplectic reduction of Courant algebroids. But at the moment it's not so important what it really is doing in detail. I will come to this later. At the moment you should just understand it as a thing which we give a certain symmetry and it spits out invariants or nice covariant objects which we can contract in a way to get invariants for this symmetry. So why is this necessary? I mean, you know, for GR, we perfectly well understand how we can construct all the invariants, right? So this was the idea behind counting these terms in the first place I gave you. So the idea usually is when we want to have invariants, we first define a covariant derivative, right, in a geometric theory. And so this covariant derivative, like here, for example, is a nabla acting on our frame, which I was showing you before. Then we have this kind of transport term here. And then we have a spin connection, which acts on the flat indices. And we have an affine connection, which acts on the curved indices. And usually we always impose the compatibility of the frame and the covariant derivative, so which in a way allows us to fix the spin connection in terms of the affine connection or the other way around. So usually what I will do is I will more look at the spin connection, but this is a matter of taste when you have this condition here imposed. And then when we have a covariant derivative, actually we can now define things like curvature tensors. So for example, the Riemann tensor, and we can also define torsion. And in GR, what we are doing is, so we are saying, okay, so we do this by taking the commutator of two covariant derivatives. And of course, you know this formula when we do this. So we get a Riemann tensor here, and we get a torsion tensor here. But you see, the left-hand side of this equation is always covariant because we are just using covariant objects. But the right-hand side actually should be only as a sum covariant. But you see, in usual normal differential geometry, some kind of miracle happens because there each individual term is covariant. And this is exactly what is not happening for generalized geometry. So in generalized geometry, we have the problem that only these two terms together are covariant, but there is no way for us really to have a nice way to define a covariant Riemann tensor, a generalized version of the Riemann tensor, which is compatible with these new symmetries I was talking about. So this is a problem. And this is exactly the first problem we need to solve to get something kind of systematic construction of this higher derivative corrections.
Certainly.
So,
Question.
yes.
And what if you consider the commutator of covariant derivatives acting on a scalar? We should get the torsion tensor.
You also get something, yes. So you will get a torsion tensor, but you still, you know, you have this problem that you cannot define the Riemann tensor here in this way. So the Riemann tensor is not really definable in generalized geometry. And the problem is that, of course, you can write down something like the Riemann tensor. You can just take the expression which you know, but then you will check this generalized diffeomorphisms and this generalized Lorentz transformations, and you will find that this thing is sick because it will not transform covariantly.
I see.
And the reason is because you should not expect that it transforms covariantly, because only the sum of it together with this torsion tensor is a nice covariant object. And in principle, they don't have to be covariant individually.
But is the torsion tensor itself covariant?
No, it is also not. It is also not itself. So this is a good point because the naive torsion tensor will also not work for generalized geometry. Very good point. So you have to change both. You have to find a new tensor for torsion, and you have to find a new tensor for curvature. And this is exactly the challenge. Torsion is not so hard. I will say a little bit more in a second about it, but Riemann curvature is in principle quite hard to find. And people were trying to do this for a long time. And I will tell you more about this in a second.
And finally, what about the last component, the non-metricity? What is the covariant for the S of?
Yeah, good point. Good point. We are always metric compatible, so there is no non-metricity here. So from this point of view, you could try to perhaps define these theories, but I will not go there. Okay, great, good, thank you. Okay, so let me wrap up the situation because so in principle, what we want to do is we want to find a way to produce nice covariant torsion tensors and curvature tensors. And to do this, actually, so this is a long-standing problem in generalized geometry. What you have to do is you have to find something which transforms nicely under this generalized Lorentz transformations and under generalized diffeomorphisms. It's not just one of them. For finding something for one of them is okay-ish, but then finding something for both of them is really, really complicated. And so the problem or the solution to this problem is actually that you should not try to find just one curvature, but you should find actually two curvatures. So this is what we actually just recently figured out, because when you just want to find one curvature, you are nearly guaranteed to lost. So why is this the case? So let me try to motivate this. Because the funny thing in generalized geometry is actually that you will get two connections. You will just get one connection, which is your usual spin connection. And here you see this alpha index is just a generalized Lorentz index. So this is usually how you would write down your spin connection as a one form valued in the Lorentz group. But so this connection alone will not work, and I will give you more details later, but you have to also add another connection, which we call rho here, and which is now antisymmetric in these two indices, which represent the generalized Lorentz group. And when you have this, so then we found a way, which is actually quite close to Cartan geometry, so that's why we call it generalized Cartan geometry, to actually write down nice covariant curvature tensors and torsion tensors for these objects. So now the objects which we have is we have our generalized frame, we have our spin connection, so this is what we know, but we get this additional new guy here. And so to do this kind of Polacek-Siegel construction or generalized Cartan geometry, what we do is we put them all into one frame on an extended space. And when you want to make the analogy with Cartan geometry, so this is our Cartan connection here. And so with this, equipped with the things, we have in a way this machine, and I will give you some details, but I don't have the time for all the details. But in principle, the only thing which you have to fix is you have to fix this ODD here, which is just the part which makes your generalized diffeomorphisms manifest. You have to fix some structure group, so this is your generalized Lorentz group. And then when you have this, so you have a nice machinery which takes this intermediate step, which is called the G Polacek-Siegel group, to give you all your invariant tensors. So this is this machine which we want to use. So at the end of the day, the only thing you really have to tell me how you get your structure group. And when you just take it to be the normal generalized Lorentz group, you will get normal two derivative supergravity for the NS-NS sector, but what I will show you today is that you can also choose this in a different way. You can choose a bigger group here, and you will get higher derivative corrections. So this is exactly what we did in the paper from the end of the last year. Okay, but let me give you some idea at least how this generalized Cartan geometry is working. And let me also check the time. Okay, so this generalized Cartan geometry and normal Cartan geometry, you actually have a Cartan connection, which is given here. And so the Cartan connection just unifies your spin connection and your frame. And so this Cartan connection can be seen as a frame under a bigger space. And then when you calculate the curvature for this frame, so what you will get is you will get your normal torsion and you will get your normal Riemann tensor. So that's the standard story in Cartan geometry. But now you see we can also introduce a generalized Cartan connection. And in principle, it mimics the form of this Cartan connection, because when you look at the first part here, it's exactly the same. But then, because you get this additional structure from this OD, D symmetry, you have to add more components. And these additional components, for example, will contain this row here. So, and then what you can do is you can also write down the corresponding curvature tensor, which I have now written down here in a less nice covariant form, because in generalized geometry, it's a little bit harder to really understand what are differential forms, but you can write it down in indices, and you use something which is called the twisted Dorfman bracket for this. And at the end of the day, you get again as components of this objects your generalized torsion, your generalized Riemann tensor, which is a curvature tensor for the spin connection here, and you also get another curvature tensor for this row field here, which is a higher curvature tensor with 3 derivatives. So this is the idea how you can use this setup to do your nice covariant tensors, which you want to use to construct your action. But now you see you have still a problem, because I still have to tell you how to choose this generalized Lorentz group, so this GS here, and also this G Polacek-Siegel. Because so these are the ingredients, and in principle, I'm free to choose them like whatever I like. And then, of course, I can make a certain choice, and I can try to check whether this reproduces the physics I would expect or not. So that means our objectives here are now to fix all these connections and all these additional fields which I was introducing by either gauge fixing or by torsion constraints. And I want to just fix them in terms of my physical fields, which are just this generalized frame fields, and of course also with in terms of their derivatives. And this is of course the same as we do in generalized in general relativity, right? Because there we also have a spin connection, but we know that the spin connection is not an independent degree of freedom, but is rather expressed in terms of the frame and derivatives of the frame, right? So this is the thing here. So that means this is a standard way of building my theory. And then, of course, what I want to do is I still want to choose this symmetry here, GS, to get just as few invariants as possible on the one hand. But on the other hand, of course, I also don't want to get too few, because I also want to reproduce the results of string theory. But ideally, I would just get one invariant, and then everything would be fixed. So this is the idea here, which I want to follow. And so what I want to show you in the next couple of minutes is actually that you can now take this G structure not just as OD cross OD as we did before, but actually I want to make it bigger, and I want to take it as OD plus P and OD plus Q. So I just want to extend it a little bit. And then, of course, this G Polacek-Siegel group also has to be extended accordingly. So that's the idea. So let me try to show you in a little bit more detail, and I'm sorry, so this part is technical, but when you really want to understand it, you cannot avoid it. So I really want to now show you how this G Polacek-Siegel is organized, because, remember I was saying it's not just OD, D, but it's something bigger. So that means what I'm doing is I want to split it, and of course it should contain the original OD, D, because so this is the symmetry which is relevant for my generalized diffeomorphisms. So I put this here in the upper component of these generators. So this is just all the different generators. But then, I also get generators which are here in the diagonal, or on the off-diagonal elements, and another generator here in the diagonal. So I just decompose it like this. And of course, this is the natural decomposition of a group OD plus P, D plus Q. Okay, and then of course, I have my generators. I know which algebra they should realize, so I just have the commutator of two of these generators. And of course, I get an eta here, and the eta is exactly the invariant matrix or the invariant metric, right? Matrix or metric, whatever you want to call it, of this OD plus P, D plus Q. So this is the setup here. And then, just for convenience, so we also introduce the structure constants of GS, so which is a subgroup, and I will tell you in a second which subgroup it is of this G Polacek-Siegel. And so these things here will be contracted with this R generators here, where the Greek indices are always raised and lowered with this kappa here, which is fully invertible. So I can always get the inverse of it, and then I have the lowered indices here, and I can use this to raise and lower indices here. So that's the idea. Okay, so now I have told you in a way what is G Polacek-Siegel. So this is the first ingredient for my construction. And the second ingredient is, of course, the structure group. So, and this G Polacek-Siegel is actually generated, as we have seen, by this generator KAB here. So this is just a normal ODD generator. And then I have some additional generators, R alpha A and R alpha beta. And so I want to understand how my structure group comes in. But you see, in principle, I was already telling you, because so the structure group should be just left moving sector times a right moving sector, like this generalized Lorentz group. So what I'm doing first is I take this generators here for this structure group and say it splits into a left moving and a right moving sector. So, and I have to relate these things here actually to these generators here. And this is hard because I have to tell you what are all these different generators, but I also want to get all of them taken into account. So what I have to do is I have to find a recursive procedure to relate them. And so the first one here is just Ka over bar B over bar. So this is just the normal generalized Lorentz generator. So this would be the OD in the product OD cross OD. And of course, this would be just for the left factor here. And I can also do this for the right factor. So I just have my first generator, and this is normal OD. But then you see, I also want to incorporate these R generators here. So they also should be somewhere there because they are an important part of G Polacek-Siegel. And so what I have to do here is I also want to put them in. So I put them in a second generator, T alpha 2. And so this thing now has just alpha 1 indices here. And so it has one R generator here and another R generator here. So you see, I'm just splitting these alpha indices, which are appearing here, in alpha 1, alpha 2, and it goes on like this. And you see, to take all the generators into account, I have to do this again and again and again, because you see here I define an alpha 2, but I only tell you what alpha 1 is. So I have to tell you what alpha 2 is, but to tell you what alpha 2 is, I need an alpha 3. And so this actually goes on and on and on forever. And so what I get is I get an infinitesimal, or sorry, not infinitesimal, but an infinite extension of my structure group, which was in the beginning just generalized Lorentz. But now I get an infinite extension of this, and I get a huge number of additional generators. And this is exactly the point where the higher derivative corrections will come in when I do it like this. So, and of course, here you also see that I can put some coefficients here, which is just the global scaling. And so this will be actually later on important because this thing here will turn into alpha prime. One thing which you see is that you have an exponential growth of generators. So there are more and more and more generators here when you do it like this. And so, but this is fine because we have, in a way, a very systematic way of constructing them. And of course, this can be also truncated at every order. And this is usually what you do when you just want to have higher derivative corrections to a certain order. Okay, so now what I have to tell you, the last thing, is how you calculate the structure constants here, because now we have fixed what is GS, but we have to calculate the structure constants as well. And the idea here is that I always take my indices here and I split my indices in two parts. And this way I can recursively define the structure constant. And you also see this here, right? Because you always have an index, for example, alpha 1 here, but you split it in two indices A and B here. You have an index alpha 2 here, but you split it into two indices alpha 1 and A, and here alpha 1 and beta here. So this is usually the way how you go from one level to the next, so that you just split one index into two. So you get something like a binary tree, actually, how these generators here are organized. And then you can do exactly the same here, and you can use this to define the structure constants. And at the end of the day, you will see again that you just turn it down to have a metric here, and the metric now is again defined by splitting these indices. And you can now calculate recursively this kappa actually here by just decomposing it into smaller kappas, which you already know. And one example, for example, is with alpha 1 and beta 1. And this is just the natural pairing which you would have on your Lorentz group or on your orthogonal group, depending on the signature which you use here. So that's the way you define this G structure group, which might look complicated, but in principle, which is completely deterministic. So you start and you have defined this group. So now that we have defined the structure group, let me check the time. Yes, so it's good. So the next thing what we have to do is we have to impose torsion constraints and gauge fixing, because so this is the way we can now really calculate our invariance. And this is, of course, what we need to, at the end of the day, write down an action. And so for this, we have to actually look at this generalized Cartan curvature. So this is this object here, where these indices actually are totally antisymmetric, and they live in the fundamental of this group G Polacek-Siegel. So that means we can actually understand that these curvatures here are, of course, coming from the spin connection, and they are coming from this row here. So these are the two connections which we have. And so what we now want to do is we want to fix all the connections we have, so the spin connection and this additional new connection, just in terms of the physical frames. So we have to find down torsion constraints and gauge fixings appropriately to be able to fix all of them. So, and this is what we are doing. You see, normally, for example, in GR, what we would do is we would set the torsion completely to 0. Here, we cannot set it completely to 0, but we can only set this following components, so which have mixed chirality to 0. But then we can also implement some additional gauge fixing, where we actually say that we only want to have mixed chiral contributions to these fields here, and all the chiral contributions here are set to 0 by a gauge fixing. So that means we are finding this consistent set here of torsion constraints and of gauge fixing constraints set up, and this will allow us to fix all these objects here just in terms of the frame which we started with and derivatives of the frame. Okay, so let me just stop here for a second, and again let me ask you whether there are some questions. Okay. Yes. So yeah. I hope I did not lose everyone, but so that's in a way you construct it. And in principle, you might see just this part here as a technical detail, because it just tells you how you construct some infinite dimensional group, which has this nice property that it seems to be exactly the right symmetry to get higher derivative corrections. So it seems to be a symmetry which knows about higher derivative corrections in string theory. So that's the basic example. And the reason why I'm giving you all these details is that you really want to see it in full explicitly. Okay, great. So when there are no questions, so then let me just explain to you a little bit how I do this distortion constraints. So for distortion constraints, now I have to find a way how I parameterize my field A here, and this A actually contains my spin connection and this row connection. So, and I have to find a way how I parameterize it, because you know that for higher derivative corrections, what you can do is you can do always field redefinitions, right? So you can bring your action and your equations of motion in different forms by doing field redefinitions. And this is exactly the analog of doing field redefinitions in this framework here. So here I say I have to define my group element, so which should be in G Polacek-Siegel, by just parameterizing this in terms of my Lie algebra generators, where actually my generators sit in this normal A here, and my group element sits in this Pascal A. So I'm just using here the exponential map. But of course, I could use any other parameterization which I like. And so in principle, here I'm trying to focus on this freedom of doing different parameterization by giving this coefficients C3, C5, and so on and so forth here. So that means I can choose them in different ways to get some kind of different parameterizations, which of course are all related at the end of the day by field redefinitions. And one of the jobs is to find these coefficients here in such a way that I get a particularly easy and nice result, which we actually have done in this paper, which appeared last year, shortly before Christmas. We have done it to this order here, where we have just fixed C3 and C5. But now actually we are just completing another paper, so where we actually have done this to all orders. So that means everything I'm telling you today just at the leading orders can be also pushed to full all orders in alpha prime, and we can construct all the things like transformations and so on, and also even the action in this framework. So that means there is really some nice progress here. But at the end of the day, then you calculate these components. So these F's here are actually the components of your Cartan curvature. You calculate them, you impose your gauge fixing and your torsion constraint, and you actually calculate what they are, and you fix them. So this is the first part of the story, and then there is another technical detail, and I don't want to torture you too much about it, because when you want to know it, you can read it in the paper, but it's still worth mentioning, because when you really want to solve these torsion constraints, you will figure actually out that you have on the left-hand side another set of generators as of the right-hand side. So that means you have to do a similarity transformations, because here on the right-hand side, you have everything expressed in this generator as tau I was showing you before. So this is one of the torsion constraints you have to solve. But on the left-hand side, you have this new generator T. And T is actually just tau shifted by this R alpha generator I was introducing before. And the funny thing is that in principle, the only thing which you have to do to relate these two is you have to do a similarity transformation. So it's just a simple change of basis. And then you can actually calculate the quantities in the new basis, so which I've written down here. So this is this kappa twiddle alpha beta, and you can of course also calculate the structure constant in this new basis, which is this F twiddle alpha beta gamma. The only problem here is, which makes it a little bit more challenging, is that I was telling you that in principle you are dealing with an infinite dimensional Lie algebra. So that means these things here are infinite dimensional things, and when you sum over all these contributions, in principle you will get infinity, and you have to find a clever way how to regularize these sums, so to get actually a nice finite results. And this is actually what we are talking about when we are saying collapsing towers, because it seems that you have an infinite number of corrections, but actually when you adjust to the leading order in alpha prime corrections, only the first orders really matter, and then the other parts of this calculation becomes redundant, but still you have to regularize it in an appropriate way. So that's why I say danger here. But you see, for you as a first order approximation, this kind of thing has to be done, but it's under control. And when you do this, you can go order by order by order. You can just calculate and do your torsion constraints. So for example, when you do the first fixing, you will find just that you get the normal spin connection here. So this expression, when you write it down in terms of frames, would be the standard candidate for the spin connection. But then you see, so you plug it in again, you use the results you had before, and now you will get a derivative. So this object here has two derivatives. And you get this 1 over g, and then this thing has also a 1 over g, so that means you get higher and higher powers also over this 1 over g, and you do it again and again and again. And so there are some nice things you can also recognize here, because other people have tried to write down higher derivative corrections, and they have identified some nice quantities in which these corrections look very natural. So for example, Linus Wolf and his PhD student Stanislav. So they have introduced a generalized Riemann tensor, so which is exactly this expression here. So you can go to your paper and you see that these expressions are actually the natural expressions which you would expect when you do this procedure. Okay, so this is the first part. So now I've yes, tortured you through the torsion constraints which you have to solve, and I've shown you that you can fix all these quantities order by order by order just in terms of this f's here, which are expressed in terms of a derivative of the standard frame and in terms of these a's here, but of course you can replace them. So that means you just really get derivatives on frames more and more and more the higher you go in order. So that means this is the first part. But then, of course, we also have to check the gauge fixing. And so the gauge fixing is chosen by killing all the chiral components of this row, of this omega here and of this row here. And you can also see that here I only use mixed chiral components. So I always have an overbar and an underbar. And the same here, right? Overbar here, underbars here, and so on and so on. So that means I only fix the mixed chiral components, because the chiral components I set 0 on the nose by gauge fixing. But of course, when I do a gauge fixing, I still have to check whether my gauge transformations still close, right? Because I still have some residual gauge fixings and gauge transformations after my gauge fixing. And so this is actually what, again, can be done in a very nice, consistent way, going order by order. So for example, I have my transformation for the A here, and I have my transformation for the E here. So, and then I can just try to fix my high order gauge parameters in such a way that I always preserve these relations here. So because this is possible, because on the right-hand side, things always depend on the lower orders, which we already have fixed. So that means we can do this step by step by step. And this actually allows us to understand how this A is here transformed, how the generalized frame here transforms. And yes, so what these kind of gauge fixed parameters there are. So let's have a look at this. So, and in principle, you know, when I do this as the first order, I will find actually that this E here, and this is actually something which you can do to all orders, has to have this simple transformation, where you now see that usually the E just should be transforming with the Lorentz rotation, but here these are the higher derivative corrections to this transformation. And so this actually, again, can be written down to all orders in alpha prime. So, and we actually have now recently just verified this, that this is really an all order alpha prime result. So this is a very simple form of this transformation. The leading order, which you will see, is that this is exactly the anomalous transformation in Lorentz, which you need for the generalized Green-Schwarz anomaly cancellation mechanism, right? I mean, generalized here because the Green-Schwarz anomaly cancellation mechanism is usually just done in the heterotic, but here you find a similar transformation also for the bosonic string, where you now have these two parameters A and B, which you set to be exactly the same. So this is also something which comes naturally out of it. And you see, so this is in principle a very nice and simple equation for the transformation. Then what you have to do is you have to collapse this towers. So this was what I was telling you before. And then you also have to insert the previous solutions from your torsion constraints and your gauge fixing. So all the things we have built up to this moment. And when you do this, for example, you can calculate this at the fourth order, so where you get now four derivative corrections to your normal Lorentz transformations, and you will first find this thing. So this is the first step where you did the first substitution, and then when you do it again, so you will actually get this result here. You see it's a very complicated transformation. And this is exactly the right transformation which you have to find these higher derivative corrections up to 6 derivatives. So that means when you use this corrected transformations and when you ask for an action, which we also can write down, but I did not do it because it would take multiple pages. So we find a unique action which is invariant under these transformations, generalized morphisms, and it has been shown that this actually reproduces the alpha prime corrections for the bosonic string and for the heterotic string. So that means at level alpha prime squared, we are completely aligned with the corrections you would get for the bosonic and for the heterotic string. And again, just to highlight for you the simplification which you get, you start with this very simple expression, which in principle, and not just in principle, but which holds to all orders. And then you plug in everything and you get this complicated mess. And of course, the higher you go in order, the more complicated it is. So this, and since I have still a little bit of time, since we started later, I can still pause and ask you guys whether there are some questions or some conceptual things I should explain.
Okay, so
Okay, I hope yes.
yes, so when we write down the transformations and we construct the AE action from it.
Yes.
How many free constants do
Yes.
we have there? Like in the action, I mean.
So for the action we only have one. Overall, there's an overall constant. So this kind of transformation fixes the action completely. And it fixes the action actually to something which is exactly the right thing, which it should be, to reproduce the string theory action at alpha prime squared, where you just get corrections for the bosonic and for the heterotic string, right? At these orders. Mm-hmm. So this is really the nice thing. And of course, you see all these components here, this F, of course, at the end of the day, you can write them down in terms of Riemann tensors and spin connections and covariant derivatives, right? So that means you can, of course, after a field redefinition, you will even further modify this expression, but it's still, of course, in general, is very complicated.
Mm-hmm. I see. Yes, and I mean A and B are general parameters of the setting, so you can't say that these are parameters.
A and B are general parameters, but of course, so these are the parameters you have to fix by comparing with actually string amplitude calculations, right? And you will fix A. It depends on the theory. When you have a heterotic string, you will, for example, set B to 0, and you identify A with alpha prime. And when you have the bosonic string, you will set A to alpha prime and B to alpha prime. So that's the way. And then you have fixed everything, and you get exactly these corrections to your normal Lorentz transformation. So this is the idea. Okay, good. So in this case, so let me just give you some remarks. And this was actually the calculation we have shown in this paper at the end of last year. So there are some technical details, right? So that we have this prescription of collapsing the towers, which in a way, is interesting because it takes an infinite number of contributions, but it reduces this to something finite. So, and then you see, so we find that when we take something else, so this is constrained. So when we would try to do some other regularization, so the residual gauge transformations would not close. So that means we really know what we have to do here. And then, of course, the invariant action can be immediately written down. So it's just more complicated. But once we have the symmetry, we can construct all the invariants and so on. And we know that this is the right symmetry. So this is the idea. And then, of course, what we know is that at the end of the day, so gauge fixing actually breaks this G structure group to something, again, which looks a little bit like OD cross OD, but this time, of course, which is highly non-linearly realized and deformed. So, and of course, this is something what you would expect from T-duality in a certain way. And then, we find this kind of deformed Lorentz transformations, which are required for generalized Green-Schwarz anomaly cancellation. And as we already were discussing, there is only one invariant action. And so this is actually completely checked at alpha prime and partially checked at alpha prime square. But now you see at the end of the day, I think also the alpha prime square results. So there has been some recent progress are fixed. So that means this is really the right thing to do. And of course, so this leaves the question open. And so this is actually what we are looking in at the moment, whether there is a way of finding other hidden symmetries which controls the full higher derivative. And at the moment, alpha prime corrections. But of course, at some point, it would be also interesting to get GS corrections for strings and membranes. And we are trying to work on this. And there are some challenges which appear at alpha prime cubed. But in principle, I mean, let me stop here. And when there are questions, we might further discuss this.
Okay, so let's thank the speaker and questions. Okay, so I will start. So actually, so I'll start from the end. So just to check, partially you mean for bosonic terms only? You mean partially checked?
This is a thing. This is a thing exactly for bosonic and for the heterotic. For the heterotic, it's a little bit easier, because you have less terms. So, and then of course you have to do the bosonic where you get these two parameters A and B. But so I think, as far as I understand from the literature, so this is checked. So this works. But then, of course, when you go, so then of course the problems start when you want to go to the type 2 string, because for the type 2 string, you know that you don't have corrections at alpha prime and alpha prime squared, but you just start with a correction which has a prefactor of theta 3 at alpha prime cubed.
I see.
So, and when you follow this logic, what you should find, and this is what happens, you should set A and B to 0 for the type 2 string. So A and B have to be 0 because they cannot give you the right corrections. But then you would assume that there is another deformation coming in. So let's call it C, for example. And so this C deformation, so in principle, should give you also then the results for the type 2 string. So that means there should be a new kind of invariant. So next to these kind of two invariants, which we have now seen, which comes with the parameter A and B, which should come at alpha prime cubed. And so this is actually what we are looking at now. So whether there is another deformation of the structure, which I've presented here, so which will give us this new invariant. So that's that we also can, for example, do the type 2 string.
So the Green-Schwarz anomaly, oh, sorry, I think Arkady raises his hand.
I need to leave, yes, sorry. Thank you very much for the talk. Yeah, thank you.
Yeah. Thank you, Arkady. Take care. Bye.
Okay, so I have a question about Green-Schwarz anomaly. sorry, not well versed in it. At which order does it start to appear exactly?
Okay, let me explain you a little bit about the Green-Schwarz anomaly cancellation. So let me just give you a very layman idea what is happening. So what you usually do is when you calculate gauge anomalies, right? So you have this kind of, I mean, in four dimension you would get triangle diagrams, right? So where you have something like fermions running in the loop. And usually, you know, when you have a theory which is not chiral, so you have fermions of both chiralities, right? And so they compensate each other. So that means these loop diagrams, so in a theory which is not chiral, so will be cancelled and everything is fine. But you know that the heterotic theory is chiral, right? Because it differentiates between left and right. So that means you have this kind of 10-dimensional version of the triangle diagram, which becomes a hexagon diagram. And this thing does not vanish, right? So you have a loop diagram which does not vanish. And that's a problem because it tells you that your gauge symmetry actually is killed by quantum corrections. So, but then what you can do is you can also find uh, a tree level diagram, and the tree level diagram actually comes from the Chern-Simons term, which you have here. So because you don't only have the H flux, right, but you also have a Chern-Simons term. So that gives you an additional coupling. And when you then calculate what you get for the B field, so you get this additional contribution here, and this will modify the tree level diagrams for the B field, which you get from your theory. And so from this tree level diagram, you will calculate exactly a contribution which will cancel your loop diagram. And this is the Green-Schwarz anomaly cancellation. But you only get this tree level diagram when you add this Chern-Simons term. But to be able to turn Simon's term and make the action nice and invariant, you have to modify your Lorentz transformation because this Chern-Simons term here actually takes the spin connection which comes from Lorentz. So that means what you will find is you find that your B field, usually your B field will not transform under Lorentz transformations, right? Because it just has curved indices. So it should not transform under Lorentz transformations. But when you actually look at higher derivative corrections, it will start to transform under Lorentz transformations. And this transformation is exactly required to get your Green-Schwarz anomaly cancellation. Without this, the Green-Schwarz anomaly cancellation would not work.
Mm-hmm. Interesting. Okay. So I had another question. What if we take supersymmetry at least in some, well, I don't know, maybe
Yes, yes,
some
it's a
we maybe construct some toy model. We take the simplest possible setting possible. So how will these generalized Lorentz symmetries behave interact with supersymmetry? Will they commute?
it's a very good question. I mean, you can in principle also use these techniques, or you could try to use these techniques to calculate corrected supersymmetry transformations. So we have not really done this, you know, because we just wanted to understand the basic steps here. But in principle, of course, you can extend these groups, all the groups I was telling you, and in principle, you could turn them into supergroups, and then they also would act directly on fermions, and you could try to understand what happens when you act on fermions. But honestly, we did not do nearly anything in this direction yet because we are just trying to understand the basics here.
I see. Okay. So, I believe, okay. So if there are no further questions, okay, let's check going once, going twice.
No, I think it's fine, and we should not torture because for you guys it's also late, right? So I don't want to destroy. I don't want to destroy your evening, so it's fine. And just in case, I mean, if anyone is interested or is thinking about these kind of things, I mean, I'm always happy when somebody is sending me an email, and I'm happy to discuss. So it's completely fine.
Perfect. So yeah, thank you very much, Falk.
Yes, thank you guys for
Yes.
having me. That was very nice.
So yes, let's thank Falk again. That was a really beautiful talk, and much appreciated.
Sorry, it was a little bit technical, but I rather short, so because you were asking explicitly about this paper, so I thought, okay, so when you ask about this paper, I will just give you the details. But yeah, okay. I mean, at least you have seen that this kind of things are sound and they have some kind of really explicit realizations. Okay.
Okay.
Good. Then thank you very much, guys. So have a nice evening, and hope to see you soon at some point in person, hopefully again.
Yeah, it was nice to see you and say hello to David.
Yes, I will. I will. Yes. So he is just in the other office next to me. Yeah, I will say hello to him. Okay, guys, take care.